Hello everybody from WCA Physics class. This is Miss Peachy, and today we are looking at Unit 3, Lesson 3. This is on speed and velocity, and we're going to talk a little bit more about resolving vectors today, and just kind of really getting more into the kinematics that are found in the early part of physics class. So again, a lot of some new stuff perhaps, some review stuff for some of you, some overlap from some of the stuff you've done in the past, some extension on that. I'll also look at some of the denotations and, you know, and that are used in your lessons and some of the differences you might see in other sources. So average speed, displacement, distance, speed, and velocity are your vocab words. You remember that displacement is a vector, whereas distance is a scalar. So vector indicates it has both magnitude and direction. In the lesson, they use the notation delta capital D. This is something I've never seen before as a representation of displacement. I oftentimes see delta x and delta y being used in displacement, so you're going to see me do it a little different sometimes just because that's kind of how I've always done it before. It doesn't really matter. Variables are there to represent something else. So whichever variables you choose is really irrelevant as long as you're consistent. So the displacement in the x direction, they have it written like this. The displacement in the y direction, they have it written like this because we're looking at two-dimensional systems. So something is moving, say, at an angle. If you're walking at an angle, you have both x displacement and y displacement to get to that point. So if I'm standing and I'm starting here and I'm walking in this direction at a 45-degree angle, my motion is really made up of both an x component and a y component. I can always break down all parallel or perpendicular motion into both x and y components, whether that be displacement or velocity or acceleration, and that's kind of the whole principle behind deriving or being able to figure out vectors, right? So that's kind of what we're going to be working on today. All right. So a couple of definitions: speed versus velocity. So speed is scalar and velocity is a vector, right? So speed is just a magnitude and velocity indicates direction of motion as well. So with velocity, we're looking at displacement, and with speed, we're just looking at distance because distance is that scalar. All right, so we have a couple of definitions here as well in this next slide. The fastest woman in the world they talk about. They talk about how she's a sprinter. It was Florence Griffith Joyner, which I remember her in the Olympics years ago. She was a sprinter, very, very fast, and ran the 100-meter dash. And so we can look at her, the distance she ran was 100 meters, but the displacement, that delta D, is the final position minus the initial position, right? And then we also give that directional indicator because she's running to the east. And that tells us, that's necessary when we're looking at a vector, that it's not just the magnitude, but also the direction she's moving. Her total distance was just 100 meters. Her total speed we can determine based on her distance divided by time, whereas velocity, we take displacement, change in displacement divided by time. And this first one is just telling us that the reason why we do this, for one, is that oftentimes you're not running at a constant speed. Your speed goes up, it goes down. So when we're looking at speed, it's an average. So when I say that speed is equal to distance divided by time, this is an average. This is not assuming constant speed. So I can figure out that I may go up in speed and down in speed throughout the journey, but the speed that this calculation of speed is just a representation of the average speed that I've been traveling on my journey. So that's what speed is. So we're not always going the same speed, throughout exactly the same speed. So that's useful. Velocities represent more of an instantaneous measure at that point. And because they give directionality, that's also important too. And some of the reasons why direction might be useful or needed, say you're doing something, they say if something is moving through a fluid, like air or water, it's important, right? Because if that air is moving around me and I'm golfing, say, and I hit my golf ball, I have to take into consideration the velocity of the wind. Not just its magnitude, but its direction, right? Because if the wind is coming straight at me, it's going to slow my ball down. It's not going to go as far, but it's not going to really affect the aim of my golf ball, assuming I'm a really good golfer, which would be a false assumption. If the wind is coming at my back, then it's going to make my golf ball go a little further, and maybe I'll have to ease up a little bit or use a different club down, so that we're not going as far. Maybe if the wind is coming at a right angle to me, I'm going to have to, hit into it a little bit so that the ball goes where I intended to go and not off course. So those things are really important, and they affect the motion of objects in reality, whether it be a golf ball or an airplane that's flying or what have you. We live in an atmosphere, so we have to take into consideration both direction and magnitude. All right, so this is where it gets a little tricky. This is practice problems with speed and velocity. So it's kind of differentiating here between speed and velocity, and it's saying that let's say you have a trip that you're going, and you are moving from your starting point, and I'm going to draw the coordinate system here as well, because that just helps me, and it will help you stay focused. We're moving 8,000 meters to the east, right? So this is like almost like a compass direction. So we have north, south, west, and east, okay? So kind of keep that in mind. Whenever we're doing a Cartesian coordinate system, we're going to use the compass directions that correspond to that. So I'm moving 8,000 meters this direction, and then I turn around and go 2,000 meters back, right? So let's actually take that one away. I'm going to go 2,000 meters back. And then I go 4,000 meters north. So it was 8,000 meters to the east, 2,000 to the west, and then 4,000 north. And I'll do that with a different color. Okay, so this is my final position right here. There. So when you look at total distance traveled, you're just adding them up. So distance traveled is going to be, remember, speed is distance divided by time, lowercase d here. So the total distance traveled is going to be 8,000 plus 2,000 plus 4,000 divided by time. We don't have time, but we can figure time out because we know how fast we're going. We know that we're actually traveling, in this case, at a constant speed, they say in the problem, of 2 meters per second. We know that the equation for speed is distance divided by time. So I can substitute, whoops, I want to get, there we go. I can substitute that 2 meters per second over here, in for speed. I know my distance, if I sum that up, is 14,000. So if I rearrange this equation, and I'm actually going to go back a little further. I can't go out anymore, but I can kind of scooch this one over. If I rearrange this equation right here, I'm going to end up with that time is equal to distance divided by speed, right? So I just flip-flop them, cross-multiplied. So I have my speed and I have my distance, 14,000. If I take distance divided by speed, oops, that should just be meters. The meters will cancel. Seconds is the inverse of, it's basically of like you have it in the denominator and it's already a fraction, so you move it up to the numerator, right? So it becomes 7,000 seconds. That's my time. And what they're saying in here is that that's the time. Like, you can't change that. Speed is different than velocity, but the time it took to do everything is the same, right? So that we know is a constant. Like, no matter if we're calculating displacement or we're calculating distance, time is time. It's not changing. So this part, I thought the next part was a little bit more confusing, and that's why I wanted to make sure I made the video for you, okay? So the next part here, they talk about, now we're gonna look at displacement or instead of distance. And we're gonna look at velocity instead of speed. And the idea here now is if I go back to my Cartesian coordinate system, and I'm gonna delete like some of this over here, just we know from our previous lesson that when we went to the east 8,000 and we went back 2,000, that the net displacement there is only 6,000, right? So we know that to be 6,000. So this is, I'm just going to erase this chunk here because that we don't need anymore. Ugh, sometimes this thing. Okay. So we know this to be 6,000. And this is 2,000. Yikes. Zoinks, as we say, right? And what we can do then is we have a resultant vector, which is here, right? That's going to be our velocity. This is our velocity vector. Well, this here is our velocity in the x direction, and this will be our velocity in the y direction. Velocity is equal to distance over time. Or the velocity in the y direction is equal to distance over time, right? So we can calculate the x and y components of velocity using that. We know that time, as we calculated earlier, was 7,000 seconds. So we calculated that when we did our speed. So that didn't change. But we do have two different equations we have to solve for. We always, when we're doing vectors, we always have to solve for the x component and then the y component. You just have to solve for both. Okay. So our x component is 6,000 meters divided by 7,000 seconds. And our y component is 2,000 meters divided by 7,000 seconds. Okay? If we divide those out, we get for our x component 0.86 meters per second. And for our y component, we get 0.57. Now we need direction. Well, when I am moving, when I look at my x component, I went 6,000 to the east and 2,000 to, I'm sorry, 8,000 to the east and 2,000 to the west. So the east, if it's a tug of war game, east won, right? Because you have more to the east than you do the west. So our net displacement in that direction is to the east. So we say that the net velocity is to the east, same direction as the displacement. And for our velocity in the, or v sub y, the velocity in the y direction, that's just north. We didn't have more than one direction there, so that's a little easier to figure out, but it's to the north. Now, at this point, this is you're just giving me the vectors, or you're giving me the vector components, the x component and the y component. We don't have the vector sum yet. That hasn't been given yet. So that's important to know that, okay, that was not given here. It does go on in, let's see here, in a next, there's like a slide that comes up after this where it tells you how to get that V, because we didn't do V here. V is right here, right? That's important. We oftentimes want to know what, hey, what is our net velocity? Not necessarily the components of each. So that's important as well, and that's coming up in the next couple of slides. So it talks about it here, basically, that the velocity then, our net velocity, is going to be the square root of v sub x squared plus v sub y squared. So we can do that. We can go on and we can take this and square it and add it to this and square it, and then take the square root of the sum of the two, basically using the Pythagorean theorem here, right, to figure out what v is. So we can do that, and we can figure out our net velocity. So let's do that. I know that's not exactly what they're doing in the lesson, which is fine because it's good to have multiple ways to practice. If you're only practicing the lesson problem and nothing else, then you pretty much know how to do that problem, and sometimes it's hard to apply it to other things. So let's go ahead and do that here. Okay. So I want to know my velocity. I'm going to take square root of v sub x squared plus v sub y squared. So that is 0.86 squared plus 0.57 squared. Let's use our calculator. By the way, if you're figuring out like you don't have a calculator, you should have a calculator. Don't just rely on your phone calculator. I use a TI-30 X. I think they're the easiest calculators to use. If you are debating buying a calculator, I would go for this. It's like 15 to 16 bucks. It's not real expensive. You do not need a graphing calculator for this class, so don't waste your money on one of those at this time unless you need it for calculus or pre-calc or something, which you already have it, which is totally fine. But if you're using your phone, it's not my favorite thing to use here. I can use it in a pinch. If you're doing this, it doesn't work. If have an iPhone, if you flip it, it'll give you a scientific calculator. If you have an Android, don't ask me because I have no idea. But let's go ahead and do this. 0.86 squared plus 0.57 squared, square root. I get 1.03. I'm going to do it one more time just to double check. 0.86 squared. So I did it on my calculator with parentheses, so I just want to make sure I did it correctly. I get 0.7396. Now, just so you know, before I will follow the rules here as far as rounding after everything's done. If you round multiple times throughout your calculation, your end result is going to have errors in it. So just round once at the very end. So that's why it's nice to be able to do this on the calculator with parentheses, so then you don't have to round. Okay. Plus 0.3249. And then square root it. Again, 1.03. In this problem, we're giving to the nearest, let's see, initially they gave us, our velocity was given to the 10,000th place, but then everything else was given to the individual. So I don't know, I guess you could round it to the nearest whole number, which would be 1. I don't know. Sometimes they don't necessarily follow all of those rounding rules. So I'm just going to round it to 1.03. If it's multiple choice, you'll need to make sure you follow the rules of rounding. Okay. And then because we're taking its velocity, it's meters per second. So that is our meters per second, and that is what V is, right? Oops. Oops. Sorry. Right here. 1 point. Okay. So remember that our V sub x was 0.86. Let me just put that on here. Just so that, because otherwise right now we just have displacement on here, and I want to make sure we have our velocities on here. And don't mix that up. Don't use velocity as one of your vector components and displacement as a different one, because they don't work that way. You have to use the same vector components. Okay, so we have what did I say? 86? This is what happens when you get over 40, ladies and gentlemen. You forget things every 5 seconds. All right, 0.86. This is 0.57 right here. And 1.03. All right, then something that we did in class, but we haven't done yet in the lesson till later, is we're going to actually figure out the angle here, because that's kind of our next natural step. So when we get the direction, it's not west, east, north, or south. It's like something in the middle. So we need to use our sine, cosine, tangent functions, our Sohcahtoa, to figure out exactly the direction here. So that's what we're going to do next. Erase, erase, erase. All right, so basically we want, zoom in, zoom over. We want this angle here. Oftentimes given Greek letter theta, just because, I don't know why, but it often is. So we want to know theta. So to figure out theta, I suggest, in this case, using tangent, because this number here was calculated using these two numbers. So it's kind of usually what I suggest using is numbers that you haven't calculated yourself, just to make sure. So these were calculated by us also, so I guess it really doesn't matter in this case, but usually we're going to use tangent here. And again, you could use sine or cosine, you just have to use the appropriate arrangement. So if you remember Sohcahtoa, let's remind ourselves what that means first, right? So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And then tangent is opposite over adjacent, right? Sohcahtoa. I actually didn't learn this acronym until I started teaching. It's funny, I never learned that in high school, but it's useful. I just memorized them. Weird, I know. All right, so we're going to use tangent. We're going to use opposite over adjacent. So the tangent of theta is equal to 0.57 over 0.86. And again, you could use sine or cosine. If you use sine, you would just use opposite over hypotenuse. You would use 0.57 over 1.03. it doesn't matter. You're still just solving for the angle of a triangle. It's very much just geometry at this point, right? Maybe some bad flashbacks for you guys. I don't know. But you'll have to get over it because we'll be doing a lot of this. In any case, let's do that. I'm just going to get rid of some of this extraneous junk over here because it kind of becomes messy. All right. So we're going to divide both sides by tangent, right? So we have that theta is equal to 0.57 divided by 0.86. I'll put that in parentheses so we know to do that first. And then we're going to take the inverse tangent of that. So on your calculator, it's the tangent to the -1 sign, which for me is a second function, which you can kind of see there. It's in yellow. Okay. So first I do is I go 0.57 divided by 0.86. And then I get a number, I hit enter, and then I hit second function and tangent, and that gives me 33.5 degrees. Make sure your calculator is set to degrees as well and not radians or grads or anything. You have to have degrees. So that you have to make sure that's set correctly. Okay. So, what did I say? 33.5 degrees. Boop, 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 move, move, move. So, let's go back to the little guy. Hey, triangle. You're not theta anymore. I figured out what your name is. Sorry. It's 33.5 degrees. Now, as far as directions go, we have to indicate compass directions. So this is 33.5 degrees to the north of east. So when you look here, here's my east, right? And I'm going north of east by 33.5 degrees. So I would say that my velocity as a final answer is 1.03 meters per second at 33.5 degrees north of east. That is my final answer right there. Okay, so you've got your velocity, which we resolved that first getting the x component of velocity, then the y component of velocity, then doing the Pythagorean theorem to get the actual velocity vector, the resultant vector, velocity vector, then using Sohcahtoa to figure out that angle and realizing that it's going north, you're moving north of east, right? We don't generally do, if I were to be doing east of north, then I would want this angle right here. But they don't usually use that one. So we don't have to worry about that. We're just going to use this one because we're moving to the north of east. Okay. Now let's see if we got everything that this lesson talked about. Resolving vectors right here. Figuring out the vector components. They actually have not yet gotten to the angles, so we're just a bit ahead, and that's okay. It's going to come up, I promise you. So I know I'm moving a little bit ahead of the lesson, which is fine, but the lesson actually is moving at a fairly slow pace, which is a good thing as well. The last thing that's talked about in this lesson has to do with graphing. So graphing motion. And we'll graph both displacement versus time, velocity versus time, and acceleration versus time. And they're going to look a little bit different. So when I do displacement versus time, which I'm going to put right here, on the y-axis we do displacement. We always put time on the x-axis, right? And so all this is showing you is that if I want to get velocity from a displacement versus time graph, I have to take the slope of the line because velocity is change in displacement over time, or here we have delta d over t, change in displacement over time. That's what velocity is. And slope is literally just y over x. Displacement is y, x is time. So the slope of a displacement versus time graph is giving us the velocity. So that's important, okay? Let's see, make sure I have everything. So when, like in this particular example here, we can see that my displacement is changing at a It's linear. So this is telling us we're traveling at a constant speed because the slope of the line is always the same. So if the slope of the line were changing, you'd have a curve, and that would indicate that we're not traveling at a constant speed. So on a displacement versus time graph, a linear slope, so constant slope, indicates constant speed. Okay, and then so, and then in this type of graph, we can calculate average speed, but we can only do it in this particular type of graph when it's a linear slope, when it's just like this, no curve to it, right? And that is the end of this part. So hopefully that makes sense to you. I think that's the end. I just want to make sure. Yes. Okay, so so displacement is total velocity times time. Right. Okay. Sorry about that. I'm just reading on to make sure that I understood what this part was asking you, but that should be pretty much it for this section. If you have any questions, let me know. Definitely encourage you to come into class on Fridays because we're going to be going through this stuff in more detail at that time. Otherwise, toodaloo, everybody. Take care. We'll see you in the next video. Have a great day.